The thesis work presented was conducted as part of a CIF funding between Optis Forensis and INRIA, under the supervision of Adrien Bousseau and George Takis, and with the collaboration of Fredo Durand and Mika Itala, and focus on lightweight material acquisition using deep learning. During the design of a 3D environment, such as this kitchen for example, artists add material information to define the style and appearance of each object. It is one of the central elements of modern rendering systems. Materials play an essential role in multiple domains such as architecture visualization, the cinema industry, or the video game industry, for example. More concretely, what we call here a material represents the light behavior on the surface of an object. When light hits a surface, part of it is absorbed, part of it is transmitted, and part of it is reflected. For my work, we were interested in evaluating how light is reflected by a surface. Traditionally, to know how a material reflects light, we can try to exhaustively measure the material from different light and view angles, as shown here. But in the context of lightweight acquisition, which was interesting to us, we wondered how much information we could extract from a single image captured with a smartphone. If we use directly the captured picture, the behavior of light is not very realistic and mostly comes from the flash visible in the picture. We therefore looked into deep neural networks to extract as much information as possible. This kind of technique relies on a large amount of training data, which we created using procedural generation of materials and different techniques for data diversity augmentation. So we created a network specialized for material extraction, to which we provided the concept of rendering. We developed a simplified differentiable renderer, which allowed us to take into account the material appearance under different lighting conditions during the training to improve the learning of our network, which allowed us to get more convincing results as illustrated here. And because our acquisition method only requires a single picture, we could capture multiple hundreds of diverse materials in a few hours. But sometimes a single picture is not enough, and other lighting conditions provide important information. We therefore proposed a method allowing to provide an arbitrary number of input pictures. We can see that the more pictures are used, the better the result, while still preserving a lightweight and convenient acquisition process. This method only requires a few pictures, and therefore allows to easily capture different surfaces, and we illustrate here a few of the dozens of materials captured during the project. But whether we provide one or multiple images, these methods require the use of a flash to capture well the light behavior on the material. And as shown on the left-hand picture, to keep the flash effect visible, one has to stay close to the surface to capture. And in some cases, the scale of the surface to capture is too big to be taken from a distance where the flash would be visible. So to avoid having to carefully capture multiple images, we propose to combine the information available in a picture with flash, for which we know how to extract the material information, with an image of the large-scale surface. The information with flash is used to specialize a neural network in a few minutes for the kind of materials available in the flash picture, before transferring this information to the large-scale image, allowing us to create materials at an arbitrary scale and resolution. But the small-scale example doesn't need to correspond perfectly to the large-scale image, providing us with some artistic freedom, such as here, where on the left we transferred the information from a gilded surface, while on the right we used a more matte material. To conclude, with this thesis, we propose different acquisition and creation methods for materials, allowing artists to create material in high definition from an arbitrary number of pictures of surfaces at different scales.